Year 10 October test, assessing general knowledge of ionic and covalent bonds. So it's going to involve answers to do with ionic and covalent bonds. It starts off saying graphite's a form of carbon and has a diagram. I can start off by trying to label the diagram and see what I can note. So firstly, we can see there are strong solid lines which represent strong covalent bonds. And between layers, it looks like something which is looking slightly less solid, which is a dotted line. So this here represents a weak force of attraction, and it's obviously going to be between layers, but we don't need to worry too much about it. The other thing we can look, if we select some carbons, in the middle, 3 bonds formed. That's something else we could see here. It says graphite's used as a lubricant. Why might it be used as a lubricant? If you've ever tried to use a pencil, you can imagine that's graphite and it leaves a mark on the paper. So why could it be used as a lubricant? You could say it's because it's soft, so the layers can slide off. Again, you could also say, looking at this diagram, what might happen if you try to move this across a piece of paper? You could say, or look at the diagram and say there's obviously weak force of attraction, so you could leave a mark on a piece of paper. So you could just say also weak forces of attraction between layers. So graphite conducts electricity. So when we ask questions about what conducts electricity, we need to think about what could possibly move. And there are only 2 things which mean that something can conduct electricity. One is if you imagine electricity moving through wires. You might know from physics that electrons move, but there are specific electrons we use or have which move in chemistry, which are called delocalized electrons. These mean electrons which are not just found in one place but can move throughout the structure. Then the other one is ionic bonding is made out of ions, because what we need for electricity to move is we need charged particles which are free to move. So let's start again. So ions, here in an ionic compound, here they obviously can't move, but we have positive and negative ions. So for example, that might be a picture representing sodium chloride. Sorry, I didn't put it properly there. So how can graphite conduct electricity? It's not an ionic compound, so we definitely can't see any ions. Now carbon, in the form of graphite, has formed 3 bonds. Now carbon normally forms 4 bonds. So what could possibly move? It's going to be the delocalized electrons, and they're free to move. So we would write delocalized electrons which are free to move. And what I was going to just say is, obviously when I collect a paper, and I would like to make sure you put all corrections on, please. Next one, C part 1. Why is graphite used for pencil leads? Again, you could think about what do we need to think about. Going back to that diagram from up here, it's very similar. If you imagine moving a pencil across a piece of paper, it leaves a mark. Why does it leave a mark? Because those layers in the diagram up here can slide over each other. So we can say layers can slide over each other, meaning that a mark over each other, so it can leave a mark on the paper. Next one, why has graphite got a high melting point? If I look at the diagram, this is trying to only represent a small part of my diagram, so I know this is a giant structure. What else do I know? It's got covalent bonds. What do I know about covalent bonds? They're strong. If you imagine trying to overcome anything which is sort of quite firmly held together, so for example the atoms in the layers, it's going to require large amounts of energy. So high melting point is going to be a large amount of thermal energy, but we don't necessarily need to say that. So we can say giant structure. So what we mean when we reject giant structure, so we can always explain. So lots of bonds, and we can also be more precise, lots of covalent bonds which are very strong, and it will require, in terms of how much energy, lots of energy to break the strong bonds. Next one, question 2. An atom or an element has the electronic structure 2882. How can you tell this element is calcium? If we add all the electrons together, we can find we have 20 electrons, which is equal to number of protons in an atom, and this is equal to atomic number. The alternative approach, which we could do here, is if we look at this, it's got 2 at the end, so element in group 2. There's lots of elements in group 2, so the other thing we could also do is look how many shells electrons, 2, 8, 8, 2, so there are 4 different shells, 2 in the first shell, 8 in the second shell, 8 in the third shell, and 2 in the last shell, and the number of shells of electrons is equal to periods and period 4. The next thing is a dot and cross diagram for chlorine. It tells us, so it's not losing focus, tells us that chlorine has the electronic structure 287, tells us that chlorine is a covalent molecule, and it says draw outer shells. So we could just start off with 2 chlorines, 7 electrons in the outer shell, 1, 2, 3, 4, 5, 6, 7. Another one, 1, 2, 3, 4, 5, 6, 7. How could they obtain full outer shells of electrons? We need to get to 8, so we could try overlapping the 2 atoms of chlorine and share. And when we form covalent bonds, we end up with a shared pair of electrons. So if we put a shared pair of electrons in here, and for each one put the other electrons back in, 1, 2, 3, 4, 5, 6, 7. For this one, 1, 2, 3, 4, 5, 6, 7. So we can see they've now got 8 electrons in the outer shell. The alternative approach might be writing group and then doing 4, 5, 6, 7, 0, and bonds, remind us how many bonds everything in groups form. Group 0 forms 0 bonds, 7, 1, 6, 2, 5, 3, group 4, 4. So we know that chlorine is in group 7, so it will form 1 bond. So if we know it forms 1 bond, imagine joining 2 chlorines together. We get a little diagram which looks like this, and this represents a shared pair of electrons. So we could put 1 pair of electrons between them. Generally speaking, if you try to do 1 pair of electrons, if you can't think of anything else, it probably will work out. The next one is asking you why sodium ions are positively charged and chloride ions are negatively charged. So what we want to do is we want to think about the basic sort of thing of where they come from when they form ions. And we could start off with a sodium atom. If we looked up in the periodic table, this is just extra information. Sodium would start off, it's got 11 protons, so it would have the electron arrangement 281. When it forms an ion, it will need to obtain, or rather it obtains a full outer shell, and the easiest way of doing this is just to lose 1 electron in the outer shell. So it could lose an electron, which is negatively charged. So if you lose something which is negatively charged, you will now have a positive charge on you. So we could phrase this as sodium atoms lose electrons. Same approach for chlorine. If we find chlorine on the periodic table, we can find it's got an atomic number of 17. So the arrangement of electrons will be 2 in the first shell, we filled that up, 8 in the second shell. First 2 always add up to 10, so how to get to 17 from 10 is 7. So that's the electron arrangement of a chlorine atom. How can it form or obtain a full outer shell? It could gain a 1 electron, so it could become Cl-, gaining configuration 288. So we could say chlorine, and it's chlorine atoms forming chloride ions. Chlorine atoms gain, you could even say 1 electron to be more precise, 1 electron, to form a negative ion, and it's called a chloride ion. So the ending changed from -ine to -ide. Diamond is a form of carbon. Look at the structure. Use structure and bonding to explain its properties. Structure. Anything that has a high melting point is going to have a giant structure. Bonding. Solid lines between atoms, so it's got covalent bonding. So how do we melt this? It's obviously going to require a large amount of energy. So we could say lots of strong covalent bonds need to be broken, which will require a large amount of energy. Diamond does not conduct electricity. Explain why. If we look at our diagram, we can see there are no ions present. Also, each carbon is formed in our diagram, if we look at the atom, 4 bonds. Carbon forms 4 bonds quite happily, so that means in its outer shell all the electrons are used for bonding. So what does it not have? It has no charged particles, as in which are free to move. So we can explain this. I've said charged particles, so no delocalized electrons or ions present. Diamond and graphite have very different properties and different uses. Diamond is used to make cutting tools. This shows a drill bit. Explain why it's used to make cutting tools. Use the table to help you. So if we look at things which we might be different for it, or even say which might be helpful, a high melting point, because if you imagine the friction involved, it will get very hot. And if you've ever used a drill, the tip usually gets really hot, so we need something which won't just suddenly melt as it's going and spinning around. And the second one, we'd also quite like something which is very hard, so it doesn't sort of like just, instead, I suppose if you use graphite, it would just leave a mark on the paper, so mark on whatever you're trying to drill. We want something which remains hard and solid. So I mean, if you have a diamond, you can actually use it to sort of scratch glass. So you could say, all you need to say for this is diamond is very hard and has a high melting point. One or two people sometimes mention does not conduct electricity. If you think most drill bits are made out of metal, that suggests that conductivity isn't an issue. So here are some atoms. Which one makes a positive ion? We could either A, use a periodic table to identify them, and if we looked it up, we'd find 281 is sodium, or if we just look, it's in group 1 of the periodic table, so we know it's a metal. 284, if we look at group 4, below carbon, that's silicon, non-metal. 287, that's chlorine, another non-metal. And 288, that's argon, non-metal, but it's got a full outer shell, and we could even put unreactive, because it's a noble gas that's in group 0, so it won't react. Which one makes a positive ion? Sodium makes a positive ion, so that's W. Which one is unreactive? That's argon, so choosing Z. Which two could react together to form an ionic bond? So we need a metal and a non-metal. The metal must be W, and the non-metal, which could gain electrons, you've definitely heard of sodium chloride, so I would go for Y. Now, I suppose you could technically go for sodium silicate, but we've not actually met, when we spoke about it, everything in group 4 doesn't actually form ions, so we need something if we want something which forms negative ions, we need something in groups 5, 6 or 7. The next little bit is another dot and cross diagram. We've got a formula here. That means it's got 1 nitrogen and 3 hydrogens present. It tells us nitrogen has the electron configuration 2, 5. It says show all the electrons, so let's start off with N. 2 in the first shell, 5 in the second shell. It's got 5, so we could imagine it needs to do something to obtain 3 more. We've got hydrogen, so non-metal, so we'll need to share 3 electrons so this can fill the outer shell. Hydrogen looks something like this. If we imagine what we do, we could have nitrogen in the middle, join it to 3 hydrogens. Hydrogens are never going to be, apart from the hydrogen molecule, joined to each other. Also, it'll never be sort of in the middle or something. So 3 hydrogens here. Hydrogen always forms single bonds. So we could put 1 pair of electrons, 2 pairs of electrons, 3 pairs of electrons. Nitrogen's in group 5. So far we've used 1, 2, 3 crosses. We need to get to 5 electrons in the outer shell, so we end up with this diagram here of ammonia. The alternative approach is if we went back to the question about groups and bonding, this one here. Nitrogen's in group 5, so that means nitrogen forms 3 bonds, hydrogen forms 1 bond, and we have 3 hydrogens each forming 1 bond, so we can combine these two here to make a displayed formulae which looks like this. We could convert that into a dot and cross diagram, as in drawing the circles around everything again. Hydrogen, 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 dot cross, because each solid line represents 1 shared pair of electrons. Remember, nitrogen's in group 5 of the periodic table, so it has 5 electrons in its outer shell. We could just put another 2 electrons in here. I almost made a mistake there. It said show all the electrons, so don't forget to include inner shells if they ask you to show all shells of electrons. Sodium chloride is an ionic compound, so this means it's made out of ions. As a solid, it will not conduct electricity. I've just drawn a little bit showing 4 ions in the ionic compound, whereas when it's dissolved in water, it does conduct electricity. These 2 diagrams might help me, they should not be touching, so that's just a bit of a mistake on my part. So here we have it in water. So when it's a solid, so as a solid, ions here, which is made up of, ions are in fixed positions and are not free to move. Whereas if we look in the liquid form, not liquid form, when it's dissolved in water, when dissolved in water, ions are free to move. Lithium fluoride is an ionic compound. It contains lithium cations. Cations mean positive ions, and ions mean negative ions. The configurations of atoms are shown. So lithium is 2, 1, fluorine is 2, 7. Show charges on the ions and also their electron arrangement. Lithium, when it forms an ion, this is just thinking if it was formed, would lose this outer shell electron, so this would disappear off. So that means this is what the configuration of a lithium ion looks like, and it would have a charge of plus. Often you draw square brackets, but this is just asked for a charge down here, so you don't need the square brackets and charge here. Fluorine has got 7 electrons in the outer shell. Again, if I was drawing it myself, I find that harder to read, but if I put them in pairs, a bit like this, I can sort of see it's got 7 and it just needs to gain 1 to obtain a full outer shell. So this outer electron is lost from a lithium, and it's so lithium atoms each lose 1 electron, and this electron is transferred to a fluorine atom, which becomes a fluoride ion. So this fluorine here looks like that, and we need to put the 7 electrons in the outer shell, which it starts with, and then it will gain 1 electron from a lithium atom, and it will now have a charge of -1, which we could put down here. You could also probably put 1 plus, 1 minus if you think that makes it clearer for you. The last question is about boron nitride, and this is just the idea of trying to make parallels, or make sort of understand and apply your knowledge to a slightly different question. If we look at boron nitride, it looks remarkably similar, in my opinion, to graphite. So any argument we can use for graphite, we could use for this. So why is it soft? It's soft because if you imagine pushing that top layer, it would slide over the different layers. So you could say weak forces of attraction between layers which are easy to break. And you could also say, obviously, layers could then slide over each other. So layers can slide over each other. Next one, why has this got a high melting point? Each one, if we look at the middle, those are forming 4, and the little or nitrogens are forming 3. So it's forming, clearly we can say there's lots of bonds. So we can say lots of strong covalent bonds which require, again, how much energy? Lots of energy to break. So once you've got your corrections in, if you could obviously put them in, and then you could hand the paper in to me, please. Thank you very much. I hope that was helpful. Do feel free to ask any questions if you have any still.